Tonight, we're going to explore the most inevitable event in all of existence. Not the death of a star, not the collision of galaxies, not even the end of Earth. Something so total, so irreversible, so cosmically final that it makes every other catastrophe in the history of the universe look like a temporary inconvenience. The day the universe goes silent. Not metaphorically silent, not quiet in the way a library is quiet. Silent in the way that the word silent stops having meaning. Silent in the way that there is nothing left to make sound, nothing left to carry it, nothing left to hear it. Silent in the way that silence itself becomes redundant because the conditions necessary to define silence, a background against which the absence of sound can be noticed, no longer exist. The universe is, right now, extraordinarily loud, not in the sense of sound waves, which require a medium and cannot travel through the vacuum of space, but in the sense of activity, energy and constant motion, stars igniting and exploding, black holes consuming matter and radiating energy, galaxies colliding and merging, particles smashing together at temperatures millions of times hotter than anything on Earth, gravitational waves rippling across billions of light years from the mergers of neutron stars, gamma ray bursts briefly outshining entire galaxies before fading into the dark. The universe is a place of extraordinary, violent, beautiful activity, and it will not always be. There is a timeline. It is written in the laws of thermodynamics, in the equations of quantum mechanics, in the mathematics of general relativity. It does not depend on any external force or any catastrophe. It follows inevitably from the way the universe is constructed. And when you trace it from where we are now to where the universe is going, you discover that the silence comes not in a single dramatic moment, but in stages, each quieter than the last, each more final, until the last possible source of activity exhausts itself and nothing remains. 7 stages of silence, each one marking the end of something the universe will never have again. By the end of tonight, you are going to understand exactly how the universe loses its voice, what goes first, what lasts longest, what the universe looks like, sounds like, feels like in its final stages, and what the silence at the end actually means for 13.8 billion years of cosmic history. Before we get started, if exploring the deep future of the cosmos is the kind of thing that pulls you in, hit like or subscribe. It costs nothing and helps us reach more minds that want to think about things like this. Now, let's begin. The year is 13.8 billion years ago. The universe is not silent. It is the opposite of silent. In the first fractions of a second after the Big Bang, the universe contains energy densities so extreme that the concepts of temperature and pressure barely apply in any familiar sense. The entire observable cosmos, everything that now spans 93 billion light-years in every direction, is compressed into a volume smaller than a proton, and it is screaming, not in sound. Sound requires pressure waves through a medium, and the concept of a medium barely has meaning in those first instants, but in energy, in radiation, in the constant, violent interaction of matter and antimatter, particle and antiparticle, creation and annihilation. The universe in its first moments is a place of maximum activity, maximum temperature, maximum energy density. Every point in space is doing something. There is not 1 cubic centimeter of the early universe that is doing nothing. For the first 380,000 years, the universe is opaque. Photons cannot travel freely. They scatter constantly off the dense plasma of charged particles, propagating only tiny distances before being absorbed and re-emitted. The universe glows brilliantly and uniformly, but no light can travel through it. Then the universe cools enough for electrons to combine with protons into neutral hydrogen atoms. The plasma becomes a gas. Photons can suddenly travel freely. The universe becomes transparent for the first time, and a flash of light propagates outward in every direction. We can still detect that light today, stretched by billions of years of cosmic expansion into the microwave range, arriving from every direction at a temperature of 2.7 degrees above absolute zero. We call it the cosmic microwave background. That flash of light is the universe's first words, the first moment it could communicate across distance, the first moment information could travel freely from one place to another. Everything since has been a conversation. Stars radiating light across the galaxy, gravitational waves propagating from massive collisions, radio signals from pulsars sweeping across the cosmos with metronomic precision. For 13.8 billion years, the universe has been talking, and then it will stop. To understand the silence, you have to understand what generates the noise, the universe's activity, its energy, its light, its gravitational waves. All of it comes ultimately from one source: disequilibrium, the difference between regions of high energy and regions of low energy. Hot things radiating heat toward cold things, high-pressure regions pushing against low-pressure regions, dense regions collapsing under gravity toward regions of lower gravitational potential. The universe began in a state of extraordinarily low entropy, not a simple, uniform state, but a very specific, very ordered configuration of matter and energy that was far from equilibrium in every way. That disequilibrium has been the universe's fuel for 13.8 billion years. The steady release of that order into disorder has powered every star, every storm, every chemical reaction, every thought. The second law of thermodynamics says entropy can only increase in a closed system. The universe is a closed system. Its entropy has been increasing since the first moment. Every star that burns converts organized nuclear energy into dispersed radiation. Every black hole that consumes matter converts it into a more disordered form that eventually, over inconceivable timescales, radiates away as Hawking radiation. Every gravitational wave that ripples through space-time carries energy away from the systems that produced it, leaving them slightly less energetic and slightly more symmetric than before. The universe is spending its entropy budget, not quickly by human standards. The budget is extraordinarily large, but it is finite, and the universe is spending it constantly, in every place, at every moment. The silence is what happens when the budget runs out. It does not run out all at once. It runs out category by category, process by process, source by source. And each category that exhausts itself is one more voice that the universe loses forever. The first silence, the end of stellar ignition. This is the silence you could, in principle, witness from a distant enough vantage point with good enough instruments, though it will take an extraordinarily long time. Right now, galaxies are forming new stars. Cold clouds of hydrogen and helium gas collapse under their own gravity, heat up as they compress, and eventually ignite nuclear fusion in their cores. The cloud becomes a star. The star radiates light and heat for millions, billions, or trillions of years, depending on its mass. And that radiation is the universe's most obvious and immediate voice. The peak of star formation in cosmic history is already behind us. It occurred about 10 billion years ago, roughly 3 billion years after the Big Bang, during an era cosmologists call cosmic noon. Galaxies were more active then, collisions more frequent, gas supplies more abundant, star formation rates hundreds of times higher than today. The universe was louder then, brighter, more violent. Since cosmic noon, star formation has been declining, not catastrophically, not suddenly, but steadily as the raw material for new stars, cold, dense gas clouds, gets used up. Stars form, burn, die, and return some material to the interstellar medium through stellar winds and supernova explosions, but not all of it. Some gets locked up in stellar remnants, white dwarfs, neutron stars, black holes. Each generation of stars returns slightly less material than it consumed. Over the next few trillion years, this process approaches its end. Star formation does not stop at some definite moment. It fades. The rate drops by factors of 10, then 100, then 1,000. The last regions to form new stars will be the densest gas clouds in the most massive galaxies where gravity is strongest and the conditions for collapse perhaps are best maintained, but even these eventually exhaust themselves. The last new star ignites. We cannot know exactly when. It depends on complex galaxy dynamics and gas availability. But sometime around 100 trillion years from now, give or take, the last cloud of gas massive enough to collapse and ignite fusion reaches the conditions for nuclear burning in its core and becomes a star. After that, no new stars form, ever. The universe will still contain the stars that exist at that moment, mostly red dwarfs, those small, cool, extraordinarily long-lived stars that burn hydrogen so slowly they can persist for trillions of years. But no new ones join them. The universe has stopped making new sources of light. The first silence is the silence of creation. The universe's womb has gone cold. The second silence, the dying of the fires. The stars that exist when the last one forms are mostly red dwarfs, small, dim, cool by stellar standards. Their surfaces glow a deep red, not the white or yellow of more massive star. They emit a fraction of the light per unit time that a star like our sun emits, but they last for unimaginable spans of time. A red dwarf with 30% of the sun's mass burns for about 2 trillion years. One with 10% of the sun's mass burns for perhaps 10 trillion years. The smallest red dwarfs, those barely massive enough to sustain fusion at all, may burn for close to 100 trillion years. Cosmic Decade 14, as astronomers tracking deep time call it, 10 to the 14th years from now. But they do burn out slowly, completely, finally, unlike sun-like stars, which develop a radiative core surrounded by a convective envelope and eventually run out of hydrogen in their core while still having it in their outer layers. Red dwarfs are fully convective. They mix their interior completely, continuously feeding all their hydrogen into the core. They burn through nearly all of it before running out. When a red dwarf finally exhausts its hydrogen fuel, it does not expand into a red giant the way our sun will. It just slowly contracts and cools. Its luminosity drops. Its color fades. It becomes what astronomers call a blue dwarf during a transitional phase as it heats up slightly with the contraction, then dims toward a cooling white dwarf state. No planetary nebula, no dramatic death, just a gradual dimming. The last red dwarf fades from visibility not in any specific moment, but across billions of years of declining output. At some point during this era, the last photon energetic enough to trigger a photochemical reaction, the last photon capable of driving biology, leaves its source and travels outward into a universe with nothing capable of absorbing it usefully. The last photon that could, in principle, warm a planet or power a leaf or be perceived by an eye, crosses a universe that no longer contains any of those things. The fires go out, not in an explosion, not in a final dramatic flare, in a long, patient, inevitable dimming that took 100 trillion years to complete and left the universe filled with stellar corpses instead of stars. The second silence is the silence of the fire. The universe no longer burns. Let's step back from the timeline for a moment and think about what this silence actually means. Right now, you can go outside on a clear night and see thousands of stars with the naked eye. Each one of those points of light is a nuclear furnace, converting millions of tons of hydrogen into helium every second, radiating the energy of those reactions across light years of space. The night sky is a map of ongoing violence and creation. In 100 trillion years, that sky is dark, not just slightly darker, completely, absolutely dark. No stars, no galaxies, just the cold remnants of a universe that once burned and has now stopped. Any civilization that survives to that era, any observer anywhere in the universe looking up at what was once a sky full of light, would see nothing. The universe has become a graveyard. White dwarfs cooling toward invisibility, neutron stars spinning down, black holes sitting in the dark, not yet large enough to dominate, not yet evaporating fast enough to be visible. The temperature of the universe by this point has dropped dramatically. The cosmic microwave background, currently at 2.7 degrees Kelvin, has cooled further with the universe's expansion. The ambient temperature of the cosmos is a tiny fraction of a degree above absolute zero. Not because anything dramatic happened, simply because the universe has expanded so much that the thermal radiation it contains has been stretched to longer and longer wavelengths, carrying less and less energy per photon. The universe has entered what cosmologists sometimes call the degenerate era, the era of stellar remnants. The light sources are gone. What remains are the ghosts, the third silence, the end of cosmic chemistry. This is a silence most people never think about because chemistry seems like such an intimate, small-scale thing compared to stars and black holes. But chemistry is the universe's most sophisticated language, the language of complexity, the language of life. Chemistry requires atoms. Atoms require stability, and stability requires the right conditions. During and after the stellar era, the interstellar medium, the thin gas between stars, contained atoms of hydrogen, helium, carbon, oxygen, nitrogen, and dozens of other elements synthesized in stellar cores and scattered by stellar deaths. These atoms could combine into molecules. They did, routinely. Complex organic molecules have been detected in interstellar space. Amino acids, simple sugars, the building blocks of chemistry, drift through the galaxy in quantities that astonish chemists who study them. But chemistry requires energy to drive reactions, and energy requires sources. In the stellar era, starlight drives photochemistry. Stellar heating creates temperature gradients. Supernova shock waves compress gas and trigger reactions. Cosmic rays from energetic events ionize atoms and initiate chemical pathways. As the stellar era ends, these energy sources diminish. The chemical reactions that depend on them slow. The cosmic chemistry laboratory goes quiet. Molecules freeze out onto dust grains and stop reacting. New chemical compounds stop forming. The complexity that starlight drove for trillions of years settles into a static equilibrium of frozen atoms in the deep cold. There is a poignant detail buried in this. The last chemical reaction in the universe will happen somewhere. A specific molecule will change its configuration for the last time. A specific bond will form or break for the last time. And then chemistry will simply stop. Not prohibited, not impossible in principle, simply lacking the energy input needed to drive it at any meaningful rate. Life, whatever forms it might have taken across the universe's history, depends on chemistry. It depends on atoms combining and separating in increasingly complex patterns, driven by energy flowing from high-energy sources toward equilibrium. When chemistry stops, life stops. When the energy gradients that drive reactions disappear, the reactions stop. The third silence is the silence of the molecules. The universe no longer speaks the language of chemistry. The fourth silence, the dissolution of matter. This is where the timeline enters territory that sounds like fantasy, but follows directly from the physics of particle decay. The proton, the positively charged particle at the heart of every atom of ordinary matter. It feels permanent. In laboratory conditions, physicists have searched for proton decay for decades and found no evidence of it. Current experimental limits suggest a proton's half-life is at least 10 to the 34th years, a number so large it makes the current age of the universe look like an eye blink. But most extensions of the standard model of particle physics predict that protons are not truly stable. The same fundamental forces that allow quarks to combine into protons also allow them, given enough time, to rearrange into lighter particles. The proton has mass. The products of its decay have less mass. The transition is energetically favorable. It just takes an almost incomprehensible amount of time to happen spontaneously. If protons decay on a timescale of around 10 to the 34th years, then somewhere between cosmic decade 30 and 40, the universe enters its most profound transformation, not from outside, from within. Every proton in every white dwarf, every neutron star remnant, every frozen dust grain drifting through the intergalactic void begins to decay, not all at once, and one by one, each proton eventually, randomly, converts into lighter particles, primarily a positron and a pion, which itself decays into photons almost immediately. The white dwarfs dissolve, not dramatically, not explosively. They simply lose proton after proton after proton over timescales that dwarf the stellar era. A white dwarf that has cooled for trillions of years and reached near absolute zero temperature gradually loses its substance to quantum probability. Each proton decay releases a small burst of energy, a tiny flash of radiation from a dying particle. By cosmic decade 40, every proton in the universe that has not fallen into a black hole has decayed. The atoms are gone. The periodic table is empty. Every element that ever existed, every compound that ever formed, every molecule that was ever part of a living thing has dissolved into radiation and leptons. Ordinary matter, the stuff of planets and stars and people and dust, exists no longer. The fourth silence is the silence of matter itself. The universe no longer has any solid substance, no atoms, no molecules, no surface anywhere in the cosmos that anything could land on or touch or build from. Just a diffuse, cooling, expanding sea of electrons, positrons, neutrinos, and photons, gradually thinning as the universe continues to expand. It is worth pausing here to appreciate what this means. Every atom in your body has a history that stretches back to the Big Bang. The hydrogen in your water molecules was forged in the first 3 minutes of the universe's existence. The carbon in your DNA was synthesized in the core of a star that lived and died before our solar system formed. The oxygen you are breathing was scattered into space by a stellar explosion billions of years ago, eventually coalescing into the gas cloud that became our sun and its planets. These atoms are ancient. They have been part of stars, part of nebulae, part of ocean water, part of countless organisms across the history of life on Earth. They are not truly yours. You are borrowing them from the universe for the brief span of your life, and they will go on after you, cycling through the Earth's systems for billions of years, eventually lost to space as the sun expands and consumes the Earth. But even those atoms scattered to the interstellar void, even the atoms that drift between galaxies for trillions of years in the long dark after the stars die, even the atoms that no observer will ever encounter again, even those are temporary. The proton does not last. The matter of the universe is itself on a timer. By cosmic decade 40, every atom that ever existed in the universe is gone. The stuff of which the universe was made for its entire observable history has been converted into radiation and dissolved. This is not the end. The silence has more stages, but this is the moment when the universe loses what we usually mean by the word material. After this, nothing is material in any familiar sense. The fifth silence, the fading of the ghosts. The black holes survive. When matter falls into a black hole, the protons in that matter are not subject to spontaneous proton decay in the usual sense. The extreme gravity of the singularity has already converted the matter into something beyond ordinary atomic structure. Black holes contain mass energy, not protons and electrons in any conventional sense. The proton decay clock does not tick for matter inside a black hole. So as proton decay eliminates all ordinary matter across cosmic decade 40, the black holes remain. Galactic center black holes containing millions or billions of solar masses. Stellar mass black holes scattered throughout what were once galaxies. Smaller black holes from various formation processes. These black holes are the universe's last concentrations of mass energy. The last objects in the cosmos that can be said to be somewhere, to have a size, to exert gravitational influence over a region of space. They are the ghosts of the universe's material past, but they are not permanent. Stephen Hawking's 1974 discovery that black holes emit thermal radiation through quantum mechanical processes at their event horizons means that black holes slowly lose mass. The smaller ones evaporate first. A black hole with the mass of our Sun has a Hawking temperature so low, about 60 nanokelvin, that it is completely negligible against the current temperature of the universe. It would take about 10 to the 67th years to evaporate. But as the universe expands and the ambient temperature of the cosmic background radiation drops below the Hawking temperature of even the smallest black holes, evaporation begins to dominate over absorption. The black holes start losing mass faster than they gain it. They start shrinking. Smaller black holes shrink faster. As a black hole loses mass, its Hawking temperature rises. As its temperature rises, it radiates more intensely. The process is self-reinforcing. A black hole losing mass gets hotter, which makes it lose mass faster, which makes it hotter still. The final moments of a black hole's evaporation are a brief, brilliant burst of high-energy radiation, a flash from something that existed for eons beyond eons. Stellar mass black holes evaporate by roughly cosmic decade 67. Supermassive black holes, those containing billions of solar masses, hold out until approximately cosmic decade 100, 10 to the 100th power years from now. 10 to the 100th power is called a googol. It is larger than the estimated number of atoms in the observable universe. It is a duration so incomprehensibly vast that every previous time scale in this story, the 100 trillion years of the stellar era, the proton decay era of cosmic decade 40, all of it fits into the first tiny fraction of the googol era. But even the googol ends. Even the most massive black holes eventually lose their last quantum of mass in a final burst of radiation. The fifth silence falls. The black holes are gone. The universe contains no concentrations of mass energy anywhere. No gravity wells, no centers, no objects, no things. Just the cooling, expanding, thinning sea of particles and radiation from all the previous stages. The universe has lost its last anchors. There is nothing left in the cosmos that could be said to be a place. The sixth silence, the heat death approaches. After the last black hole evaporates, what remains? Electrons and positrons, neutrinos, photons stretched by expansion to wavelengths so long their individual energies are almost unimaginably small. Perhaps a few other stable particles, depending on which extensions of the standard model are correct. These particles continue to exist. They continue to move, but they are moving through an expanding universe that is growing larger and emptier with every passing eon. The average distance between particles increases constantly. The probability of any two particles encountering each other, already extraordinarily small after the matter era, continues to decrease. At some point, the particle density becomes so low and the expansion so relentless that even the interactions between electrons and positrons, which would normally annihilate each other into photons, become vanishingly rare, simply because the particles never find each other. The universe is not prohibiting these reactions. It is just making them geometrically improbable by separating everything from everything else. The photons continue to travel at the speed of light. They always will. but their wavelengths continue to grow with the expansion of the universe. Each photon's energy declines. The photon field becomes more and more dilute, the photons more and more separated, the energy per unit volume decreasing towards zero. The universe is approaching what physicists call the heat death. Not a violent end, not a cataclysm, the maximum entropy state, a condition where energy is distributed as uniformly as possible, where no temperature gradients exist to drive any process, where no disequilibrium remains to power any reaction, where nothing is happening and nothing can happen because there is no source of order to be converted into activity. The temperature of the universe asymptotically approaches absolute zero, not because it ever quite reaches absolute zero, but because the energy that remains is so spread out, so diluted, so dispersed across such enormous expanding volumes that the effective temperature is a number with so many zeros after the decimal point that the distinction between it and zero is purely mathematical. Nothing is doing anything. Not because physics prohibits it, because there is nothing to drive it. The second law of thermodynamics has won. Entropy is at its maximum. The universe has reached equilibrium. The sixth silence is the silence of thermodynamics. The universe has run out of disequilibrium. There is no longer any difference between any two regions. No flow of energy, no process, no change. But here is something that takes careful thought to fully appreciate. Absolute silence is not the same as absolute stillness. Even in the maximum entropy state, even after the heat death has been achieved, even in a universe with no stars, no matter, no black holes, no temperature gradients, quantum mechanics does not go quiet. The quantum vacuum, the state of lowest possible energy in a quantum field, is not truly empty. It fluctuates. Virtual particle pairs continuously appear and disappear. The uncertainty principle guarantees that energy at any point in space cannot be precisely zero, because that would require simultaneously knowing both the energy and the time at perfect precision. The vacuum hums with quantum fluctuations. These fluctuations are real. They have measurable consequences. The Casimir effect, where two metal plates placed very close together experience an attractive force from the different spectrum of vacuum fluctuations between them versus outside them, has been experimentally confirmed. In a universe at maximum entropy with no other sources of energy, these quantum fluctuations are not silent. They are the last whisper of a universe that has otherwise fallen completely still. They carry no information, they drive no processes, they accomplish nothing, but they exist. And over time scales that make the Google look like an instant, something extraordinary becomes possible. Quantum fluctuations are random, and given sufficient time, any configuration that is not absolutely prohibited by a conservation law will eventually occur through random fluctuation, including, in principle, ordered configurations. A momentary fluctuation that produces a region of locally lower entropy, a brief concentration of energy in a small volume, a spontaneous arrangement of particles into an ordered structure. The most extreme version of this idea is the Boltzmann brane. Named for the 19th century physicist Ludwig Boltzmann, who first considered the statistical mechanics implications of a maximum entropy universe. The idea is that, given infinite or near infinite time, even a fully equilibrated universe will occasionally produce, purely by random fluctuation, a self-aware structure. A brain in the loosest sense. an arrangement of matter and energy, complex enough to have a momentary experience before dissolving back into the vacuum. The probability of any such event at any given moment is unimaginably small. But in a universe with infinite time, an unimaginably small probability per unit time becomes, given enough time, a certainty. This is deeply unsettling philosophically. It means the universe never achieves absolute silence. In its maximum entropy state, it produces an infinite sequence of random fluctuations, most of them trivial, some of them over time scales beyond any numbering system that has a name, producing momentary ordered structures that dissolve again instantly. The universe's final voice is random noise, quantum static, meaningless, uncaused by any prior event in any meaningful sense. Simply the baseline chatter of a quantum vacuum that cannot, even in principle, be completely silenced. The seventh and final silence. The question of time itself. This is the most profound stage, and it is the one that requires leaving behind almost every intuition we have about what silence means. What is silence? At the most basic level, silence is the absence of sound. But more abstractly, silence is the absence of meaningful signal. Silence is a state in which nothing is communicating anything to anything else, in which no information is being transmitted, in which no change is distinguishable from any other change. In the maximum entropy universe, is time still passing? In physics, time is not simply a background clock ticking away regardless of what happens. Time is measured by the occurrence of events, by the sequence of distinct physical states. When a particle decays, that is an event and time has passed. When a photon is absorbed, that is an event and time has passed. When a quantum fluctuation occurs, that is an event and time has passed. But as the universe's particle density approaches zero and the probability of any two particles interacting approaches zero, the events become extraordinarily rare. The time between events grows without bound. In the most extreme limit, if the universe is finite in volume and has reached maximum entropy with no remaining particles, there are no events at all. Time, in the physical sense of a sequence of distinguishable states, ceases to have meaning. The concept of before and after requires that two states be distinguishable. If the universe is in exactly the same state at what we would call two different moments, the concept of those being different moments loses physical content. Time does not stop exactly. It becomes undefined, like asking for the temperature of a system with no particles. Temperature is defined as the average kinetic energy of particles. A system with no particles has no temperature, not zero temperature, no temperature. In the same way, a universe with no events has no time, not infinite time, no time. This is the seventh silence, not the silence of no sound, the silence of no change, the silence of no distinction. The silence in which the concept of silence itself, as the absence of something that was once present, becomes incoherent because there is no longer anything that was once present to be absent. The universe does not end, in the sense that a physical system occupying a state does not simply vanish, but it ceases to be a universe in any meaningful sense. It ceases to be a place where anything happens, a time when anything occurs, a stage on which any story unfolds. The conversation that began 13.8 billion years ago with the first free photons of the universe ends not with a final word, but with the slow dissolution of the very concept of words, speakers, and listeners. This timeline raises questions that physics can frame, but cannot fully answer. One of them is about the nature of the silence itself. In human experience, silence is always defined against a background of potential sound. You notice silence because you have experienced sound. The absence is meaningful only because the presence was once real. Silence in a room where no one has ever spoken, in a cave that no creature has ever entered, feels different from silence after music has ended. The latter carries the echo of what was. The former is simply neutral. What kind of silence is the universe's final state? On one hand, it is the silence after extraordinary sound. The universe was loud for an almost incomprehensible duration. For 100 trillion years, stars burned and exploded and collided. For longer still, black holes slowly evaporated in brief terminal bursts. For longer even than that, the remnant radiation drifted and redshifted through an expanding void. The universe has been doing things for so long that the concept of its history dwarfs anything we have language to describe. On the other hand, in the deepest possible physical sense, there is no one to remember the sound. No echo survives in any accessible form. The information about everything that ever happened in the universe is, by the time of the heat death, so thoroughly scrambled and dispersed that recovering it would be impossible even in principle. The stars, the galaxies, the civilizations, the thoughts, all of it is encoded in the correlations between particles, so separated and so diluted that no reconstruction is conceivable. The universe's silence is not the silence of a concert hall after the last note fades and the audience holds its breath. It is the silence of a state in which the concert, the hall, the audience, and the concept of sound have all dissolved into undifferentiated static, and the static itself has faded below any threshold of meaning. Let us come back to the human scale for a moment, because these time scales are so vast that they risk becoming abstract. You exist right now in the loudest chapter of the universe's history. Not the absolute loudest. That was the Big Bang and the first billion years of chaotic star formation. But you exist in the bright, active, productive era when the universe is still doing most of its interesting work. Stars are burning in every galaxy. Planets are forming. Chemistry is happening. Life, at least on this planet and perhaps on countless others, is evolving and thinking and looking up at the sky. The cosmic microwave background, the first light of the universe, is still warm enough to be detected. The galaxies are still visible. The laws of physics are still producing the full range of processes they are capable of producing. This is the era of maximum complexity, maximum diversity, maximum richness of physical phenomena. The silence comes later, much later, after timescales so vast that they make the current age of the universe look like the first heartbeat of a very long life. After our sun has died and Earth is gone, after the Milky Way has merged with Andromeda and that merged galaxy has aged and dimmed, after the last stars have faded, after proton decay has dissolved the last atom, after the last black hole has evaporated in its final brilliant burst, you're not living in the dying universe. You're living in the universe's most active era, cosmologically speaking. The silence is not imminent. By any human measure, by any civilizational measure, by any measure that means anything to a creature whose lifespan is decades, the universe is extraordinarily loud right now. But on cosmic timescales, the silence is coming, It follows from the laws of physics as inevitably as the fall of a stone follows from gravity. The thermodynamic arrow of time points from the ordered past to the disordered future, and the future is long. The Voyager spacecraft, which we explored in a previous video, illustrates something important about this timeline. Voyager 1 is currently the most distant human-made object in the universe. It crossed the heliopause, the boundary where the sun's influence gives way to interstellar space, in 2012. It is now in true interstellar space, drifting through the very medium whose properties we spent years predicting and getting wrong. By the mid-2030s at the latest, Voyager 1 will go silent, not because it has been destroyed, because its nuclear power source, the radioactive decay of plutonium in its radioisotope thermoelectric generators, will have decayed too far to power even the minimal systems needed to communicate with Earth. The spacecraft will keep drifting, it will be intact, but it will no longer speak. Voyager's silence is a tiny preview of the universal silence to come. A human-made object, built with extraordinary care and ingenuity, carrying a golden record with music and images and greetings from a species that wondered about its place in the cosmos, drifting silently through the interstellar void. No longer transmitting, no longer connected to anything, moving through a universe that grows larger and emptier around it. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. It will not enter that star's planetary system. It will just drift past, silent and cold, carrying its message through a region where no one will receive it. In 1 trillion years, if it has not been destroyed by collision, Voyager 1 will still be drifting through whatever the universe has become by then. The protons in its aluminum and gold and copper will eventually decay. Its mass will dissolve into radiation. The golden record's grooves, etched in physical matter, will cease to exist. Voyager is the universe in miniature, active for a brief span, silent for incomparably longer, eventually dissolved into the formlessness that awaits everything. There is a way to look at the 7 stages of silence not as loss, but as a complete story. Every universe that is thermodynamically interesting, that has disequilibrium, that has processes and activity and change, is also a universe that is spending its ordered state. The very things that make a universe interesting, stars, chemistry, life, thought, are the processes by which a universe converts its initial low-entropy state into the high-entropy equilibrium that is its final state. The interesting universe is the dying universe. The activity and the silence are not in opposition. One is the process of becoming the other. From this perspective, the universe's silence is not a failure. It is a completion. The universe began in a state of extraordinary order, which physics calls low entropy, and it has been doing the work of redistributing that order ever since. Stars are engines for converting nuclear order into dispersed radiation. Chemistry is a mechanism for converting chemical order into thermal energy. Life is an extraordinarily efficient and complex method of locally increasing order while globally increasing disorder. Every living thing, every thought, every civilization is a temporary eddy in the flow from order to disorder. A brief local structure that maintains itself for a time before dissolving into the equilibrium that surrounds it. The silence is the completion of a process that began with the Big Bang. a process that the universe has been engaged in for its entire history. The entropy budget is spent. The ordered state has been fully converted into the disordered state. The work is done. Carl Sagan wrote that we are made of star stuff. It is true. The atoms in your body were synthesized in stellar cores and scattered by stellar explosions before condensing into the solar system and eventually into you. You are the universe looking at itself, briefly and locally. You are the ordered state examining its own orderliness before returning to equilibrium. The silence is not the universe giving up. It is the universe finishing what it started. What does the silence mean for the question of meaning itself? This is a question physics cannot answer. It is a question philosophy and perhaps poetry must address. But physics can frame it. The universe will be silent for incomparably longer than it was loud. The stellar era spans about 100 trillion years. The time from the end of the stellar era to the heat death spans a Google years or more. The ratio of the silent era to the loud era is a number so large it has no name. Does this mean the loud era was insignificant? Does it mean that stars and galaxies and life and thought were just brief fluctuations in a universe that was always on its way to silence? In a thermodynamic sense, perhaps. The low entropy initial state was always destined to evolve toward maximum entropy. The stars were always going to burn out. The black holes were always going to evaporate. The matter was always going to decay. The processes that produced life and thought and civilization were always temporary expressions of a dissipating order. But the thermodynamic perspective is not the only perspective. The universe does not have a perspective. It does not evaluate its own history. It does not consider the stellar era brief or the silent era long. It simply evolves according to its physical laws. The concepts of significance and meaning are not properties of the universe. They are properties of the observers within it. And observers, brief as they are in the cosmic timeline, are real. Their experiences are real. Their thoughts, however temporary the physical substrate that produces them, are genuine events in the universe's history. The fact that those events are temporary does not make them less real while they occur any more than a symphony is less real because it ends. The universe will go silent. But it was not always silent. For 13.8 billion years and for 100 trillion years to come, it spoke in stars and gravity waves and electromagnetic radiation and chemistry and the extraordinary, improbable complexity of living things that wondered about their own existence. That speaking happened. It is written into the universe's causal history in a way that cannot be undone. Even when the matter is gone and the radiation has faded and the black holes have evaporated and the universe has reached maximum entropy, the fact that the speaking occurred is a fact about the universe's history that is, in a precise physical sense, real. The silence does not erase what came before it. A final accounting, 7 stages, 7 silences, each one marking the end of something the universe will never have again. The silence of creation, when the last new star ignites and no more are born. The silence of the fires, when the last red dwarf fades from its trillion-year burn into cold darkness. The silence of chemistry, when the last chemical reaction drives the last molecular change in a universe losing its energy gradients. The silence of matter, when proton decay dissolves the last atom and ordinary substance ceases to exist. the silence of the ghosts. When the last black hole evaporates in its final burst of Hawking radiation, and the universe's last concentration of mass energy is released into the void, the silence of thermodynamics, when the heat death approaches and the universe achieves maximum entropy with no remaining disequilibrium to drive any process, and the silence of time itself, when events become so rare and so undifferentiated that the concept of time ceases to have physical meaning. These silences do not happen in a day. They happen across time scales that make the current age of the universe look like the blink of an eye. The universe has not been dying since the Big Bang. It has been living loudly and brilliantly and violently, and it will continue to live more quietly with each passing era for durations that dwarf anything we have words for. But the silences come, each one absolute, each one permanent, each one subsuming the voices that came before it into a darkness from which they do not return. And here, in the loudest era the universe will ever see after cosmic noon, in the brief window when stars still burn and galaxies still spiral and planets still orbit and life is still possible and minds can still look up and ask what they are looking at. Here is where we stand. We are the universe in its talkative phase. We are the part of the cosmos that grew complex enough to hear itself, to ask about its own past and future, to map the trajectory from the first light to the last silence. We are surrounded by the evidence of 13.8 billion years of cosmic speaking. In every direction, light from ancient stars and distant galaxies, gravitational waves from collisions that happened before our sun was born, the faint microwave echo of the universe's first moment of transparency. The universe's history is written in the light that reaches us from every direction, and we have built the instruments to read it. The silence is coming, not today, not in any time frame that threatens anything we know or love. But it is coming with the same certainty as the sunrise and the tides, following from the same laws that govern the falling of every stone and the burning of every star. And we are the part of the universe that knows it. That knowing is itself a form of speaking. A voice the universe did not have for its first 9 billion years and may not have again after our time. A brief, improbable, cosmically unlikely capacity to look at the stars and understand what they are and where they are going and what it means that they will one day stop. The universe will go silent. But right now, listening to the light of 100 billion galaxies, reading the history written in the cosmic microwave background, detecting the gravitational waves of emerging black holes, sending our own voices out into the interstellar medium on golden records aboard spacecraft built with the technology of a young and curious species. Right now, the universe is speaking, and we are listening. That will have to be enough. And it is.